So the first talk is on astrophysical and atmospheric neutrinos by Spencer Klein from Berkeley. So please, Spencer, the floor is yours. Go ahead.
Thank you, and I'd like to thank the organizers for this kind invitation to speak. My charge was astrophysical and atmospheric neutrinos. Since I have a rather short amount of time, the atmospheric neutrinos got the short end of the stick. Just wasn't that much more to say about them. So I will start out by talking about astrophysical neutrinos, discuss the diffuse astrophysical neutrinos, discuss how we are moving toward finding astrophysical sources. Then I'll talk about particle physics from high energy natural neutrinos and give some perspective looking ahead. I will quote a fair number of statistical significances in the talk, and throughout I'm going to try and only give post-trial significances. So as many of you know, astrophysical neutrinos are believed to be produced in the beam dumps of astrophysical accelerators. The likely mechanism is Fermi acceleration, where the particles repeatedly bounce off of shock fronts and get accelerated. There certainly have been many more exotic mechanisms proposed. They seem less likely. Hopefully Olivier Deligny will talk more about this. One prediction of Fermi acceleration is you get an energy spectrum of the protons, the number of protons, the energy goes, the energy of the -2. This becomes somewhat softer and more sophisticated models. Then you have these protons slam into a beam dump, which could either be matter, probably mostly protons, or photons. These two possibilities lead to different charge pion charge ratios and energy spectra. So one of the main things you can learn from diffuse neutrino is something about what this beam dump is. And I'll come back to that when I talk about the data. And then at high energy, you have another production mechanism which can occur en route when a high energy cosmic ray proton interacts with a photon from the cosmic microwave background radiation, forms a delta plus, which then decays, giving you neutrinos. Kind of, you can see here, all of the mechanisms are very similar. It's a question of where they are and what the target is. So there's a very broad energy spectrum of natural neutrinos shown here in the bottom. I'm going to concentrate on the right portion of the plot. There are atmospheric neutrinos. These are neutrinos produced in cosmic ray air showers. You produce pions, which then decay, giving you muons, which then decay, giving you more muons. These are fairly well understood, but are useful for doing neutrino physics to study neutrino interactions and properties. And they're also a background to atmospheric neutrino, to astrophysical neutrinos. As you can see, the spectrum is steeper. So if you go to high enough energies, the astrophysical neutrinos should dominate. And then there are these cosmogenic neutrinos from this so-called GZK neutrino mechanism, where you have the delta plus at the highest energies. So I'll covering this region mostly. The current experimental landscape at the, I'll call it the very high energy region, consists of 3 experiments. Here, the grandfather of them in some sense is IceCube, which is deployed in the Antarctic ice at the South Pole. It's got 5,160 sensors covering a cubic kilometer. It's been running as a full detector since 2010. There's the deep core dense infill, which gives it a smaller section with a lower energy threshold. And there's this dense pack upgrade in progress. That is being joined by an experiment in Lake Baikal called GVD. Of course, there was a smaller experiment in Lake Baikal that's been going back as long as IceCube, but now there's a major upgrade. It currently consists of 2,300 sensors and 0.4 cubic kilometers. By 2024, it should have 4,000 sensors and 1.5 cubic kilometers. And then there's KM3net in the Mediterranean Sea. This has 2 sites. I will also mention this has more sophisticated sensors with multiple phototubes in them. So per sensor, it is more powerful than the others. There is ORCA, which is a dense pack array specifically designed to measure the neutrino mass hierarchy. It's currently 180 sensors. The full detector will be 2,120 sensors and 0.07 cubic kilometers, so threshold in a few GeV region. And then the large array ARCA, which is now 144 sensors deployed, will be 4,140 sensors and 1.1 cubic kilometers. So these are kind of the full versions are somewhat comparable in size. And if you I don't have time to go into more detailed comparisons. So the signatures for astrophysical neutrinos are very varied. At high energies, there's a number of different signatures for neutrinos. You can have interactions that are contained within the detector. These are usually called starting events. You can have contained cascades like shown here. This covers all flavors, neutral current interactions, and electron neutrinos and most tau neutrinos, charge current interactions. You have the whole event, so you have good energy resolution, but the directional information is moderate to poor. You can have starting tracks, so you have a cascade with a track coming out. These are new charge current interactions, and here you get moderate energy resolution because part of the muon typically escapes the detector, and good directional information. Then you can have through-going muons from new mu charge current interactions. Here you have this beautiful track, so you have excellent directional information, often much better than a degree, but the energy resolution is very poor because you have to measure the muon track, and based on the stochastic energy loss, there's uncertainties there, and more importantly, you don't know how far outside the detector the interaction occurred, so you don't know how much energy the muon lost before it reached the detector, and you don't know the inelasticity. You can also have these tau double bang events like this, where you see one from the interaction, second from tau decay. And then other point I would make are the main backgrounds are atmospheric muons and neutrinos. Of course, atmospheric muons are downgoing or misreconstructed. They're very numerous. Big way to get rid of them is to look for upward going tracks and or look for starting events. And then there's the atmospheric neutrinos you have to contend with, and there one of the big tools is the energy spectrum. So this is an analysis of through-going muons from IceCube. It comprises 650,000 upward-going muons from neutrinos in 9.5 years of IceCube data. We take the muon energy proxy, could also do this with neutrino energy, but muon energy is more directly observable, and the zenith angle distribution, and fit it to a sum of conventional and prompt atmospheric neutrinos, small background of misreconstructed atmospheric muons, and astrophysical neutrinos. We do a 2D fit in this energy proxy and zenith angle. And you can see here on the right-hand plot showing the muon energy proxy, and energy is above sometimes 10 to the 5th GeV. The astrophysical neutrinos dominate, and so they stick out here, and that's where we get our astrophysical neutrino measurement. And we can fit that to a single power law. We can also consider more complicated models. They're somewhat favored, but not needed. And by somewhat favored, essentially something that's convex downward seems to be a bit better fit to the data. If we do look at the single power law comparison, this lets us compare it with a number of other studies of astrophysical neutrinos. And this plot here shows comparison in terms of the spectral index for the single power law versus the flux. Typically, we use 100 TeV as the pivot point because that's roughly in the middle of our sensitivity. And you can see there's the 3 points. These sort of more prominent blue points are this analysis I've just talked about. There's also an Antares cascade and tracks analysis shown here, an IceCube analysis of starting tracks labeled as inelasticity, and then the IceCube cascades analysis shown here. And you can see there's a somewhat of a range of spectral indices between 2.3 and about 2.9 for the best fit results. And there's some tension between the different results. But if you look more closely, you can see these are different samples of different flavor ratios and cover different energy ranges. It's not yet a big concern, although it is certainly something we're looking at. The other thing we have looked at are looking at the astrophysical neutrino flavor ratios. Astrophysical neutrinos are believed to be very far away, so they are kind of sort of in the infinite length limit when it comes to oscillations. And what this means is that no matter what composition you start with at a source, there's plenty of time for it to oscillate, and you end up with something relatively close to 1 to 1 to 1 at Earth. These colored points here show different combinations. The red point is kind of the standard one where the pions and muons are allowed to decay freely. We also consider the possibility of starting with a neutron beam only, or cases where the muons either lose energy via synchrotron radiation before decaying, or they could be accelerated before they decay. But so you see there is some sensitivity to accelerators, but we're not there yet. There are a couple of different measurements on this plot. One is one where we identify new tau events by looking for the double bang or double pulse signature. Double pulse means we have these two cascades that I showed you earlier, but they're close enough together, you can't really separate them. However, for some of the optical sensors, the light from the two cascades will arrive at a different time, giving you two peaks in the light output. And so these are waveforms shown from a double pulse signature event. And to show you, like in this DOM here in the upper right, you can see fairly clearly there are two separate pulses of light from the two separate cascades. And this is sort of currently our main method for trying to measure the flavor ratio. We have some others, though. We can look at starting traps and measure the inelasticity distribution sensitive to the new tau new mu ratio. And of course, we can compare cascades and tracks. This gives us information on the new E abundance. And probably in a few years, we'll be able to say something about accelerator models. We're not there yet, though. We also are interested in looking at the new bar ratio. There are two tools to do that. I'll talk about one here. It's the glass shell resonance, where an antineutrino comes in, interacts with an atomic electron, and produces a W boson. For electron at rest, this requires a 6.03 PeV, 6.3 PeV neutrino. IceCube sees one event, partially contained hadronic shower. Its visible energy in electromagnetic equivalent is about 6.05 PeV. When you account for the difference between electromagnetic and hadronic energy, this is right on the ratio on the 6.3 PeV resonance. The significance from the energy alone to be a glass shell event is about 2.3 sigma, and that was sort of what was defined initially. But there's also some early light seen in the shower, consistent with muon production in the shower. That would tell you it's got to be a hadronic shower, not electromagnetic. That increases the significance somewhat. And here, it's only one event, can't say much, but with more, we can measure the new bar ratio. There's also some information looking at the inelasticity distributions of events. So turning to source searches, there are a number of strategies. You can look in the whole sky for point sources, either for constant or variable or episodic sources. There's many models for that. You can search for catalogs of likely objects, active galactic nuclei, supernova remnants, you name it. There's a huge number of possibilities, either constant sources or variable episodic. You can also do searches looking for specific events that are triggered by high emission observed, for example, in X-rays or gamma rays, or even optically. And you can look at individual sources. You can do stacked sources, looking for emissions from classes of events. You can do searches that are sort of triggered by other observatories. And the one couple of messages to make on it is, there are many possible free parameters in how you do the search. There's these. You can also optimize your search for hard or soft spectra. And, it's critical. And of course, we do it, fix the parameters before unblinding. And there's lots of discussions here about trade-offs between the number of trials factors for very broad search versus the breadth of the search. Where do you want to, at what point do you want to test? And of course, now a lot of the data is public. And so in addition to analyses by by IceCube, we also have analyses by outside theorists. I'm going to focus on I'll call them hints or evidence for positive emission, for seeing emission from sources. I just want to make you aware there are a large number of searches that did not find anything, much larger number. So keep that in mind as you look at our evidence. So this shows the latest IceCube sky map. Got 1.13 million upward going muons in 10 years of IceCube data. That's more than in the diffuse search, because if you're doing a sky map, you can tolerate more background and looser cuts to get more events. Of course, these are mostly atmospheric neutrinos, but that's the nature of it. Angular resolution is pretty good. It's less than half a degree for energies above 10 TeV, and no significant point sources are been seen. Of course, every map has to have a hottest spot on it somewhere. For IceCube, this is shown right here. It's happens to be 0.35 degrees from NGC 1068, which, as I'll show you, is an interesting source. It's got a significance of 2.9 sigma after trials factor. So NGC 1068 happens to be one of the more interesting possibilities. It's an active galactic nuclei. That means it's a galaxy with a supermassive black hole at its center that's accreting material, so it can emit high energy particles. It's also pretty close. It's 14.4 megaparsecs from Earth, which for an object like this is quite close. Give you another metric of that. The redshift is 0.0039. Said observed with a significance of 2.9 sigma. If you fit the energy spectrum, you get something quite soft. The spectral index is about -3.2. This just shows you a plot of NGC 1068 in the optical region on the left and the neutrinos on the right. And the colors show the neutrino intensity, and this X shows where the source is. The other indication of possible source is TXS 0506. I suspect a lot of you have heard of this before. It's a blazar. That means it's an active galactic nuclei that's emitting a relativistic jet, which is pointed nearly at Earth. This is believed to be one of the most likely possible source classes for producing neutrinos. We know it produces high energy gamma rays. This source is somewhat further away, 1.65 gigaparsecs from Earth, or a redshift of 0.3365. Again, for a blazar, this is relatively close. And there are two interesting pieces of evidence. In September 2017, we observed a 290 TeV neutrino coming from the direction of TSX 0506. And this happened to be during a coincidence, during a period when there was emitting high fluence of gamma rays, i.e. flaring. This coincidence has a 3 sigma significance by itself, and then 3 sigmas after trials for other IceCube alerts. This led to a couple of ex post facto searches for neutrino emission from the source. A later analysis found a 158-day flare, 2014 to 2015, unaccompanied by enhanced gamma ray emission. So something to keep in mind. It had a significance of 2.5 to 3.5 sigma, depending on analysis. This is maybe lower than you have heard before. In fact, the lower significance is from a newer analysis. The reference is given here. And the main reason for the change in significance is there were a couple of events that did not make the cuts for the second analysis, and indeed looking probably should not have. Anyway, the plot on the left shows the 290 TeV event for the 50% containment area and 90% containment area, and it's superimposed on a plot showing the GeV gamma ray emission as seen by the Fermi telescope. This here on the right shows the neutrino light curves from the later analysis, and you can see this curve here is TXSO506, this first flare, and the second analysis also found a second flare centered around the 290 TeV event. And you can see they look reasonably impressive, but there are other sources that have shown similar flaring. And so the significance is not that large. So what do we know about astrophysical neutrinos? One is the flux appears isotropic. That tells us they are predominantly not from our galaxy. Same time, autocorrelation studies show that there are many, and I wrote here more than about 50. One could read other numbers, and I don't have time to go into the details. Sources. So whatever the sources are, they're relatively common. We've set limits on emission for many source classes. I don't have time to talk about that. We do have evidence of emission from active galactic nuclei. There are the two sources that I've mentioned. There's also a recent STACK study that looked at 32,000 active galactic nuclei and finds 2.6 sigma evidence for emission from AGN as a whole. That study looked at multiple scenarios. The most significant evidence is for neutrino emission proportional to the accretion disk luminosity in the infrared band. The other thing to keep in mind is, most of these analyses look for emission from various source classes. It's among other things, a way to keep the trials factors down compared to an all-sky search. But quenched sources, these would be opaque to photons, so dark to photons are also possible. But because of this trials factor issue, they're harder to find. There's another. Okay, I will speed up. Possible source of emission is from dark matter, which can build up and annihilate, producing neutrinos. Rate depends on the mass and annihilation mode. This can happen in many places. Perhaps the most interesting is the sun. Sun is mostly hydrogen, so probes spin-dependent couplings. These show the most recent limits as a function of dark matter energy and cross-section here. And you can see that neutrinos are currently the most sensitive way to look for these things. We also use these neutrinos to do neutrino physics. Typical thing is to fit a 2D matrix of neutrino energy, muon energy, some other proxy and zenith angle, and fit to various models. We've done that, for example, here we show the neutrino absorption cross-section in the Earth. The plot on the right shows neutrino vacuum and matter-induced oscillations, and compared with various experiments. The two notice are this light blue measurement from IceCube, showing it's competitive with other experiments. This large red circle is from Orca, which I mentioned. This is, again, just partially deployed, and a year of data, eventually be 3 and then 10 years. You can see it's already an interesting measurement. And then this dark curve here shows what Orca expects to do. You can also look for sterile neutrinos, etc. I want to spend a few minutes talking about higher energy neutrinos. And experiments like the existing ones, IceCube and KM3Net and GVD, are good up to about 10 to the 16th EV. If you want to go higher in energy, you need a much larger detector, and I'm talking more than 100 cubic kilometers. Optical Cherenkov doesn't work for that, so you need a new technique, and that new technique seems to be coherent radio Cherenkov emission. If you go down to low frequencies, long wavelengths, it becomes Cherenkov radiation becomes coherent. You add the amplitudes, then the pulse power goes as the neutrino energy squared. This gives you thresholds above 10 to the 17th EV or order of it, and you can go below that with phased array techniques. you need a non-conducting medium like Antarctic or Greenland ice. There you get absorption lengths ranging from many hundreds of meters to more than a kilometer. You can put detectors on a 1 kilometer spacing and build a very large detector. And I want to point out, you can actually measure the neutrino direction from this using the radio spectrum and the polarization. One experiment that is doing that, and there are a number, I'm picking on this one because it is funded to build the detector that's large enough that it has a decent shot to see a neutrino signal. It's called RNOG. It's a radio detection experiment at Summit Station in Greenland. There, the logistics may be easier than Antarctica. They're funded to build 35 stations with an effective volume of order 10 cubic kilometers. As of last summer, they had deployed 3 stations, builds on the Antarctic experience of Ariana and Ara, and they will have a combination of surface antennas here and the antennas buried 100 meters deep. There are also Earth skimming experiments. These are cases where you look for a tau neutrino that comes through, goes through the Earth in a short cord, produces a tau, which then escapes and makes it out into the atmosphere before decaying. So you see an upward going shower. A number of experiments are looking for that. One of them, which is looking for that and other things, is the Anita balloon experiment shown here. It floats above Antarctica at about 35 kilometers altitude. Looks out using these horn antennas out to the horizon threshold, so you can see up to 600 kilometers away. The downside of that long range is you have a higher threshold. It's very soft and fuzzy, but 10 to the 18th, 10 to the 19th EV. You can also see cosmic ray air showers. Polarization gives the shower direction up or down. The interesting thing is they've observed these anomalous showers that appear to be going upward, but the path length through the Earth is incompatible with standard model physics. Just the chances of absorption are too high. This could be new physics, atmospheric effects, or something else. Also, on their 4th flight, they observed 4 Earth skimming events, which are consistent with tau neutrinos. The interesting thing here is the imputed flux you get from either of these observations far exceeds the limits from other experiments. A lot of people have spent time thinking about this, either beyond standard model physics or probably something much more prosaic. Looking ahead, in the short term, we look forward to the completion of KM3net and Baikal GVD. They'll give a big boost of sensitivity in the southern sky. Unlike IceCube, which is at the South Pole, their acceptance sweeps through the sky. Orca should be of particular interest here, expects to find the neutrino mass hierarchy to somewhere between 2.5 and 5 sigma, depending on the various angles, in 3 years. These experiments have better angular resolution than IceCube, because there's less optical scattering in water, boosts their sensitivity. IceCube is putting in a 7-string upgrade, which will have much smaller spacing and improved optical modules, giving it a threshold of a few GeV. And importantly, it will have many calibration devices to calibrate the whole array, should give better angular resolution for the whole detector, so higher sensitivity. And I don't want to give dates because of COVID, which has really thrown the whole Antarctic program for everything into a tailspin. Looking ahead, further ahead, we expect to have IceCube Generation 2. This will be roughly an 8 cubic kilometer optical Cherenkov array with the surface array to cover the optical footprint. This is important to reject atmospheric neutrinos that are accompanied by air showers and get a purer astrophysical signal. Should also have a 1,600 kilometer cube sternator and aperture radio detection array to study these higher energy neutrinos. This is, sort of more than 10 times larger than RNOG. There are a number of experiments proposed to look at radio detection. There's also the P1 array in the Pacific Ocean and multiple Earth skimming efforts. So my conclusions: optical Cherenkov neutrino telescopes have collected million event samples of atmospheric and astrophysical neutrinos. We observed diffuse astrophysical neutrinos at energies from about 10 TeV to 10 PeV at the flux near the maximum expected based on photon emission. You know, and of course that maximum is based on photon emission, so quenched sources could be stronger. They're largely isotropic, indicating that there are a large number of sources, mostly outside our galaxy. There's evidence that some or most of these neutrinos may come from active galactic nuclei. The natural neutrinos have been used to study neutrino oscillations, including sterile neutrinos, measure the interaction cross-section at TeV and even PeV energies and inelasticity distribution, and look for a wide variety of beyond standard model processes. Looking ahead, more powerful optical and radio Cherenkov telescopes should come online in the next decade and show us the ultra-high energy neutrino universe. Thank you. I'm happy to answer any questions.
Thank you for the nice coverage of high energy neutrino world. So questions, please. Everything was clear. If I may ask a question, you mentioned the spectral indices with some spread and possible explanation as different mixture of flavors. How big spread is expected for different flavors?
That depends on the model. I mean, in the model we mostly use a single power law, there should be no difference. So yes, then these should all be, you know, all be the same. But there are a lot of things that could be going on. One of is I mentioned, you know, that, you know, more complex models that are convex downward are somewhat favored. And if you had that, then you could end up with a spread because you're looking at different energy ranges here. Or if the flavor ratios changed a bit with energy, you would also get a spread. And it's also—
so it's more energy than flavor.
Energy is easier to understand how you would get it. And also, you know, this is attention. They're not radically different, you know.
Yeah, I agree. It's not different. I was just thinking of the mechanism behind. Okay, thank you.
Sure.
Are there any other questions? I can't see any. So thank you very much. And now we move to neutrino phenomenology, which will be presented by Pedro Machado.
All right, let me see if
please
I can share my screen. Okay, can you see my screen?
Yes, but not full screen.
All right.
Now it's okay. So please go ahead.
Okay, so first, thanks the organizer for the invitation to speak. So I decided to add a little bit on my title. I added new ideas and opportunities in neutrino phenomenology. So what I'm going to talk about is about some novel ideas and approach on neutrino phenomenology. For most of this, I have been motivated by the liquid argon technology, but the things I'm going to talk about, especially the main idea, can surely be applied to other detectors. And the aim here, in a nutshell, is to leverage neutrino experiments to their fullest, okay? To exploit the detector capabilities, such as like topological reconstruction in large TPCs, or to take advantage of the high intensity beams and their setups, et cetera, et cetera. So before I tell you exactly the new things that I want to say, let me just give you some context, right? So the usual business in neutrino phenomenology has been, you know, coming up with a pipeline, like relying on a pipeline that essentially boils down to solve an integral. You compare some observed event spectrum to whatever event spectra you would expect if there is new physics. So in a nutshell, you do something like this. You have some event spectrum that is defined by some fluxes, some cross sections, some probabilities, something that describes how well you reconstruct the neutrino energy, and a bunch of experimental details like efficiency, etc. Okay. This is what have been people have been using for several studies like non-standard interactions, sterile neutrinos, neutrino decays, etc. I'm not going to talk about this stuff here, okay? So if you want to hear about this stuff, you can sleep for half an hour. There's nothing wrong with this approach that I just described it here, but what I'm proposing is to take one step further into the capabilities of neutrino experiments, into the nitty-gritty actually of neutrino experiments, and try to do physics with that. So let me give you two examples instead of being speaking on the three examples instead of speaking on the abstract, okay? So the first example is sub-GeV atmospheric neutrinos. So in a nutshell, so this is a work that I did in collaboration with these three junior folks and Stephen Park. Throughout this talk, I'm only going to show pictures of my collaborators who do not have a job, a permanent job. So the idea here in sub-GeV atmospheric neutrinos is the following. Regarding oscillation physics, is one of the richest samples we ever will have access to, okay? If you look here, the CP violation, for instance, can be seen by the difference between the purple line and the green line. This is neutrino energy, oscillation probability for different zenith angles. And you see that the absolute difference here when you vary the CP phase can easily be of like 10%. To put things in context, in the beam, in the Dune beam, for instance, the absolute difference is about 1 to 2%. So CP violation in sub-GeV atmospheric neutrinos is 10 times larger CP violation in beam neutrinos. And the reason is very simple to understand. If you just take the oscillation probability in vacuum, there is a piece of it which violates CP, which can be written as this, where this is the reduced Yarskog, so all mixed angles are here, the sign of the CP phase. And these are the signs of the oscillation phases, okay? So for beam neutrinos, they are at atmospheric distances. So these phases here are like pi over 2. So these two signs here are like 1. But this guy here is underdeveloped. It's basically about pi over 2 over 30, which is like 1 over 20. Okay, so have a 1 over 20 factor, and this explains why the CP violation at Dune it's like few percent, right? 1 to 2%. If you look at this at sub-GeV atmospheric neutrinos, these two phases here are oscillating very fast, so they are averaged out. So this averages out to a half, and the solar phase is about pi over 2, so the sign is 1. So we are talking about half compared to 1 over 20. So the CP violation in sub-GeV atmospherics is 10 times larger the CP violation in beam neutrinos. So the obvious question is then why do we actually have the beam, right? And the reason is very simple, is that CP violation, well, sub-GeV atmospheric neutrinos is actually very, very hard to probe. And the reason is the following. If you see here these oscillation probabilities, you see that it strongly depends on the zenith angle, where the neutrino comes from. So you need to reconstruct the neutrino direction, okay? When the neutrino comes and interacts with the nucleus, you typically emit a lepton, a charged lepton, and you might emit a nucleon out of the nucleus, okay? So if you look at big detectors like Super Kamiokande, Cherenkov detectors, if these neutrinos are below 1 GeV, these protons here, these outgoing protons are also below 1 GeV, and they don't emit Cherenkov light. So if they don't emit Cherenkov light, you only have the lepton here, and that makes the direction determination of the neutrino very, very hard. But liquid argon TPCs can do it, and here's what I mean by that. Just in a nutshell, a liquid argon TPC is a bubble chamber, but it's colored. And by colored, I mean it has colorimetry, so every different particle exhibits a different colorimetric signature. And as opposed to the old bubble chambers, these detectors can actually be submitted to like high intensities. Okay, bubble chambers can't. So a small liquid argon TPC detector called Argonaut here at Fermilab showed us that this technology can detect like 20 MeV recoil protons. Okay, 20 MeV kinetic energy. And by detect, I mean reconstruct the track, identify it as a proton, and point in the right direction. For comparison, if you look at Super K, protons can only emit Cherenkov light if they have energy above like 1.4 GeV, okay? And the topology of an event carries a lot of information on it. For example, this in the same detector in Argonaut, it has been shown that neutrino events tend to emit more protons, have a higher proton multiplicity than antineutrino events. And this can be understood if you just look at the hard interaction where neutrinos tend to kick out a proton, which leaves a track in the detector, but antineutrinos tend to kick out a neutron, which is essentially invisible in these detectors, okay? Making a long story short, if I take, just for as an example, a 300 MeV neutrino coming from zenith angle, say 0, and I try to reconstruct it without detecting the protons, so this is an event where you have no protons and no pions in the final state, just a lepton. This is the spread you get in energy, which is pretty bad, but in zenith is crazy, right? It basically can come from anywhere. If you detect the proton, then this spread becomes much, much smaller. And interestingly, this spread here is comparable to the size, to the angular size of the core of the Earth, okay? Making a long story short, we do a very complicated simulation, all details, et cetera, et cetera. For the aficionados, you can look at here, you can look here. I put small letters so that the non-aficionados cannot read. But the final result is the following. If we forget the beam at all, we just look at the sub-GeV atmospheric neutrino sample in Dune, and we assume that the true value of delta CP is what is preferred currently by T2K, we can see that atmospheric neutrinos alone at Dune can actually rule out certain values of CP violation above 3 sigma. And this is very interesting. Again, for context, we can compare to Hyperkamiokande. This is from the Hyperkamiokande proposal. Here they assume a different CP value, true CP value 0, but it doesn't change much. The point is Dune can be as sensitive or even more sensitive than Hyper-K. Now, this can be a bit counterintuitive because Hyper-K is like 5 times larger than Dune, right? The detector is supposed to be 5 times larger than Dune, but because atmospheric neutrinos, they follow a power law like energy to the minus 2.7 or so, the number of events, useful events with directionality that you can have at Dune for the sub-GeV actually compensates the fact that Dune is much smaller. So the number of events in these two detectors is actually fairly comparable, okay? And as a bonus, you can actually, if you measure CP violation with the beam itself, you can use atmospheric neutrinos to do Earth tomography. I'm only going to show you this slide, but basically, if you leverage everything that the detector can give you, you can do Earth tomography measuring the core of the Earth at better than 10% precision. Okay, so this is basically a simplified model of the Earth with 3 layers: core, lower mantle, and upper mantle. Whatever color is this, orange lines. They are basically the constraints that we can put if we consider the total mass of the Earth measurement and the measurement of the moment of inertia, which are like at the 10 to the minus 4 level. So we shouldn't ignore that. Okay, but better than 10% is something that was never done before with neutrinos, and this is interesting because it's highly complementary to tomography measurements with quakes. Okay, but enough of that. So the take-home message here is that if you exploit the particular features of the experiment, it opens up in unique opportunities. In the case of Dune, we could do the first ever study of sub-GeV atmospheric neutrinos with directionality. It gives you an independent determination of the CP phase from the beam and a powerful Earth tomography measurement. And overall, one step further into experimental capabilities means new opportunities. Okay, so let's go to a second example, which is dark neutrinos and alternative explanations of the mini-Boone anomaly. So we heard yesterday from David Caratelli about the micro-Boone experiment and the mini-Boone anomaly. But just to remind you, mini-Boone saw an excess of events compared to the background. It was a beam of mu neutrinos, and it saw an excess of nui, of electron-like events, which is actually almost a 5 sigma anomaly with respect to the theory expectations here. Now, David showed us that the obvious candidate to explain that is stellar neutrinos, where a nu mu oscillates to a nu e in the small baseline that they propagate in mini-Boone. But there is a strong tension when you try to explain all experimental data with stellar neutrinos. Okay, so basically the appearance measurements prefer this region, this appearance prefers whatever's to the left of the blue lines. And this is a 3 sigma preferred region. So there's a big tension there. So the opposite explanations do not work. How do we explain this data? Well, we take a step back and we look at the experiment again. Minibone is a mineral oil detector where they rely on the Cherenkov pattern, the Cherenkov light pattern, to identify particles. So for example, when a muon traverses the detector, it gives you a pattern which is like a disk. When an electron traverses the detector, it gives you a pattern that's like a fuzzy ring. And photons are invisible unless they convert to any plus and minus pair in the detector. And then a plus and minus pair basically gives you a fuzzy ring. So pi knots, for instance, which would emit 2 photons, if the 2 photons convert, you would have 2 overlapping, well, perhaps overlapping fuzzy rings. But if these 2 fuzzy rings are on top of each other, it's very hard to distinguish from a single one, okay? So how do we explain the excess leveraging the details of the experiment? So let me take a step back and tell you about the model. So this is a work I did in collaboration with Sudip Jana and Enrico Bertuzzo and Renato Funchal. So the idea here in the model side is that neutrino masses could come from a dark sector. And because of mixings between neutrinos and particles in the dark sector and between the gauge bosons of the dark sector in our photon, the neutrinos become a portal to new physics. So in a nutshell, the idea is that you have a dark photon, you have a breaking of the dark photon, you have a dark sector with some new physics like dark photon. You have a breaking of the symmetry that gives you mass to this new gauge boson. And by mixing, this propagates not only to neutrino masses, but also to neutrino interactions, okay? In a nutshell, what happens in this kind of model is that the neutrinos could upscatter to these dark neutrinos, let me call that way, via these dark Z's. And this only happens because of mixins in several regions, in several places in the model. The dark neutrinos would decay to a neutrino and a Z dark. And the Z dark, because of the mixing with the photon, would go to a plus and minus. If this plus and minus is sufficiently collimated, it cannot be distinguished from an electron, and Minibone would classify it as an electron-like event. So the nice thing about this model is that the UV completion actually relates to the neutrino mass mechanism, and the model explains the Minibone data fairly well, okay? There are several other possibilities. So you can play with the model spectra. You can change a little bit the model for transition magnetic moments, scalar mediation, et cetera. But the point is, in the pheno side, there are a few things that can happen that can help you distinguish these models from each other, or search for some specific model. That this basically include things like the a plus and minus pair explaining Minibone, or maybe it's just a single photon. The plus and minus pair opening angles, different amount of hadronic activity, which for Minibone is useless, but for experiments like microbone is very, very useful. Coherent enhancements, that means that you could have more events in detectors of argon compared to carbon, and so on and so forth, okay? So there has been a push, this I stole from Asli Abdullahi, who is a postdoc at Fermilab. There has been a push to get all these models and classify them not as models, but classify them according to signatures. And the signatures would go like one shower, one track, and perhaps a gap. So making a long story short, there are several signatures that maps into several models differently, and understanding the details of the detector and the details of the models gives you the opportunity to probe new physics, okay? Now, backgrounds depend on specifics of the model and the experiments, but a major thing is the neutrino nucleus interaction model. The handles also depend on the experiment and the realization of the model. And there are potential searches essentially everywhere in the SBN program, in T2K near detector, in IceCube even, et cetera, okay? So the take-home message here is that if you understand the experimental details, you can actually have novel proposals for explaining the anomaly. And this naturally leads to a rich program spanning several experiments, technologies, and models with UV completions, et cetera, et cetera. So again, one step further in the experimental capabilities means new opportunities, okay? Now, for my last example, I have actually a special participation here. I hope it works. Let me just real quick stop sharing and share again with share sound and optimize for video clip. I hope this works. Okay, so I have a special participation of a PhD student from the University of Chicago, Nina Coyle.
Hi, everyone. The next topic has to do with near detector tuning and neutrino beamline experiments. And the basic idea is the following. When you're doing a physics analysis in a neutrino experiment, of course, you want to be able to model the neutrino nucleus interactions within your detector. But we don't necessarily have a good handle on all of the different processes. And so the way that beamline experiments approach this issue is to do near detector tuning, in which they place a smaller version of the physics detector very close to the beam source, sometimes just a kilometer away. And then they adjust the generator model to match the near detector observed data. Now, there are a number of new physics searches that are proposed at the near detector in order to take advantage of the higher statistics at the near detector. And so the question we wanted to ask is, does this near detector tuning affect new physics searches at near detectors? And does this tuning affect different signatures in different ways?
All right, very good. Thank you, Nina, virtually. So yes, this is the question we want to ask. How does the neutrino nucleus interaction modeling impacts new physics searches? So before we go there, let's ask how bad is our understanding of the neutrino nucleus interaction. And there was a recent paper by the class collaboration and the E4Nu collaboration. So essentially, in a nutshell, there is an experiment at JLab where an electron beam hits a target. Here I'm going to focus on the carbon-12 target, and whatever comes out is detected in this beautiful detector here. And what they do is that they try to reconstruct the incoming electron energy. They know the incoming electron energy, but they try to reconstruct it by mimicking what is done in neutrino experiments. And in doing that, they also compare to predictions from neutrino event generators, okay? So their data are these dots around here with the arrow bars, and they compare to two different generators. One is the black line, and the other one is the black dashed line. And you see that the agreement is bad, right? We have like disagreements at the order of, I don't know, maybe 30% there. It's so large that it's kind of silly to talk about 20 to 30%. It's just very, very bad, okay? So how do neutrino experiments deal with this mismodeling? Well, they do tuning, okay? But tuning is just a word. What exactly do they tune? Do they tune, okay? So let's take NOVA as a case study, and we'll look at the tuning and see what we learned from that. So NOVA recently published a paper where they showed that, they basically showed they described the tuning procedure. So they first show that the generator does not describe well the data. So this is an output, well, two outputs, the red and the dotted black curve histograms. These are two outputs of the Gini generator with two different models for the meson exchange current component. And you see here that you are actually quite far from the data for both cases. So what they do is that they argue that, in a nutshell, that this MEC component, this meson exchange current, it's also known as 2P2H. This is fairly badly known. It's quite uncertain. So they reweight the MEC component of the cross section in the plane of Q naught and Q vector, where Q naught is basically the visible hadronic energy, and Q vector is the momentum transfer, okay, which can be reconstructed from the mu1 energy, mu1 angle, hadronic energy. And what I want you to see here is that this weight, the scale here goes from 0 to 5. Okay, so this is not a small reweighting. This is a gigantic reweighting. It can change this component of the cross section by almost an order of magnitude. Okay. Now the obvious question is, well, if you do that, does this tuning wash out new physics signatures in neutrino experiments? I cannot give you this answer in general. I need to look at model by model because the signatures are different for different models. So I'll take two cases as examples here. But in general, what we do is the following. We first simulate mock data with new physics, okay? Then we tune the generator to that mock data, assuming in the generator that there is no new physics. So in some sense, this is mimicking a possibility that we find new physics in the experiment, but our generator has no new physics. When we tune, do we still see the new physics effect or not? Okay, so is the new physics signature is still there? Now, let's take the first case, stellar neutrinos. So the signal of the signature of stellar neutrinos are wiggles in the neutrino energy, essentially the spectrum of neutrino energy. And if you do the near to far ratio, before any tuning, just compare what you would see theoretically, you would see the green curve and you clearly see the wiggles here, okay? Now, when you do the tuning, the near to far ratio post-tuning would look like this black line here, okay? So we see that the wiggles kind of move it a little bit, but you can still see the wiggles. Like this really looks like stellar neutrinos. So the verdict for this case is that the tuning does not wash out the signature, and that's very good. Okay, that is mostly because there is near to far differences, right? But anyhow, it does not wash out. Now let's look at case 2. Case 2 is a neutrinophilic scalar, so the model boils down to this, where basically a neutrino can Bremsstrahlung a scalar that decays to neutrinos or leaves the detector or decays to dark matter, so it's invisible. So essentially, it gives you an excess of missing energy in a neutrino detector. Okay. So here I'm showing you the spectrum of missing energy. The blue histogram is for the standard model background. Just when neutrinos scatter in the nucleus, there is missing energy. Like neutrons, for instance, would be missing energy. And you see that there is a large excess for the standard model. There is a large amount of missing energy for the standard model around here. If you put a signal, you get this, I don't know what color is that, maybe orange, maybe magenta, pink, whatever. You get this guy here. So pre-tune data over standard expectation would be this black line here, okay? So you see that there is indeed an excess of missing energy due to the new physics model at around 500 MeV. But then when you perform the near detector tuning, what happens is that cross-section will get reweighted, etc. You use that to see what happens here when we do the post-tune data over expectation. What happens is very interesting is this, where the excess of missing energy is completely gone where it was there, but it now became a deficit of missing energy. And this is the opposite experimental signature. So the tuning changes this case very, very, very dramatically, okay? It tells you that an excess of missing energy becomes now, after tuning, a deficit of missing energy. Now, the obvious question is, what happens to experimental sensitivities? And unfortunately, I do not have that to show you because this is work in progress, so stay tuned. But the take-home message here is that understanding the details of the analysis procedure, the nitty-gritty of it, may reveal that certain BSM searches, they need to be done with great care, accounting for this tuning procedure and all that. But others are fairly robust, like stellar neutrinos. The point is that without these details, some sensitivity estimates are just wishful thinking. So again, one step further into the experimental capabilities gives you new opportunities. There are several other examples that I could go through here, but I do not have time, like light dark matter in neutrino experiments, tau neutrino detection, milli-charged particles, neutrino electron meson resonant production, like the glacial resonance, but with rhos and pions, and so on and so forth. Okay, but since I'm running out of time, I wanted to finish this with some reflections. So we are living in an era of precision neutrino physics, right? The era has arrived already. And precision means new opportunities. But it seems to me that to benefit from these opportunities, we need to leverage the unique capabilities of neutrino detectors specifically, and we need to explore the model signatures in great detail, okay? In my humble opinion, this can only happen if we have a vibrant collaboration between theorists and experimentalists, because it's very hard for theorists to understand the unique capabilities of neutrino detectors, and it might be hard for experimentalists to accrete all model signatures given the number of models that are in the market and all the different things that could happen to that. But in general, this will expand the physics program of the neutrino experiments, and it will push both theory and experiment to their fullest. Okay. Of course, this is easier said than done because neutrino experiments are extremely non-trivial in terms of their capabilities, reconstruction, etc., and they are all different. So I guess I can stop here. Thank you.
Thank you. So are there any questions? The perspective of these different searches is very interesting. So maybe, yeah, please go.
Yeah, so I actually had a question for Pedro. I was curious about the interaction between theorists and experimentalists. Could you maybe elaborate on what sorts of data products you're able to get right now from these different neutrino experiments, and maybe what you wish you might be able to get?
So this is currently a work in progress as well. But recently we had what was supposed to be a mini workshop between, it's called the SBN theory mini workshop. So this is a meeting that I organized together with, we basically put together theorists and experimentalists. And the rule for experimentalists is that nobody cares about pictures of you cleaning your PMTs. And the rule for theorists is that nobody cares about the details of the stability. Oh, is there any other question? Yeah, so the rule for theory is that nobody cares about the details of the stability of your scalar potential and these details, right? So the goal is to get experimentalists and theorists together and discuss new things and get new ideas. This mini workshop, we're discussing prospects for, let me share my screen again, for discussing strategies for these searches. Okay, so actually this is where I took the Asley and friends slides. And the mini workshop had 100 people. So there is a lot of interest in pushing experiment theory collaboration in the neutrino side. But this is still very much work in progress, like exactly wish lists, for instance, from one side to the other, we are currently defining that actually. So I'm sorry, I don't have like a concrete answer to you, but I guess here things are evolving so quickly that the devil is in the details, right? So if I had to make you a list of deliverables right now, I don't know if I could make one that is honest and you know, reasonable.
But you see the chance. Okay, any other questions? I can't see any. So thank you very much. And now we move to the theory of neutrinos. And I would like to ask Joseph Valle from University of Valencia to give us the theory outlook. Please go ahead.
Hello, do you see my slides?
Yes, we see, but it's not full screen.
Now?
Now it is.
Okay. Hello, everyone. First, I wish to thank the organizers for the invitation. My task is to give an overview of illustrating how neutrinos may guide our steps beyond the standard model and what could be the associated signals at high energy collisions. So I start from neutrino oscillations. Out of all natural neutrino sources, solar and atmospheric neutrino have provided us the discovery site for neutrino oscillations, which marked a new era in particle physics. Following these discoveries experiments, we have had the reactor and accelerator-based studies, which have not only confirmed the oscillation phenomenon, but also improved the parameter determination. So much so that we now have a pretty decent determination here along the diagonal, the chi-square maps, determining all 6 oscillation parameters. And you also see the parameter correlations, very, very useful for theorists, for model builders. By and large, the data are pretty much consistent with the three neutrino paradigm, except for three loose ends. The first concerns the ordering of the neutrino mass spectrum. You have two solutions corresponding to normal and inverted ordering. Then you have the octant of the atmospheric mixing. Again, you have two solutions. And finally, a very poor determination of delta CP. These three loose ends form the target of the next generation of experiments. And I'll give you an example of Dune, which is meant to determine delta CP, to discover CP, leptonic CP violation. And indeed, it will do so, at least over a large chunk of parameter space, except perhaps if neutrinos get their mass from mixing with some heavy neutrino. In this case, there is additional CP violation associated to this mixing, which can get confused with CP violation coming from the three neutrino paradigm. So this degrades the CP determination sensitivity, but still it is a problem which is not really fatal and can be circumvented, at least partially. I'll give you a recent example here, not from Dune, but from the European spallation source. You see the CP discovery sensitivity versus the value of the CP phase. In black, you have the standard case with unitary leptomixing matrix. In dashed, you have the degradation due to unitarity violation. It's not really a disaster. Now I move to interpretation, starting from TBM for 3B maximal. This is just a numerological neutrino mixing ansatz, which captures the most essential features of oscillations. You have bi-maximal atmospheric mixing, tri-maximal solar mixing, zero reactor mixing, and hence no CP violation. While no longer viable, this pattern can be systematically generalized by exploiting symmetries so as to produce revamped mixing schemes which are not only viable, but also predictive. There is a whole class of them. This is just one example. You see here two predictions for the oscillation parameters, which map into this green band that you see in the right, in the down plot. And this overlaps the 90% confidence region obtained by global oscillation fit over a narrow range of delta CP, indicating predictivity of these answers. A different neutrino mixing pattern is the so-called bi-large. The idea here is that the largest quark mixing angle, namely Cabibo, is similar in magnitude to the smallest of the lepton mixing angles, namely the reactor angle, suggesting that perhaps one can use this small parameter, the Cabibo angle, as a universal seed for flavor mixing. And in this case, the mixing matrix are expanded as power series on this small parameter lambda. So if you know lambda, you know them all. And indeed, this is what you see here, the prediction in blue for the atmospheric mixing and in black for the solar mixing. A very, very tight prediction, given the fact that TET13 is so well measured. And I should say, these are just two classes. You have the bi-large lepton mixing class and the generalized TBM class. There are other neutrino mixing hypotheses. The good news is that many of them can be probed in the next round of experiment, such as Dune. But I now move to neutrinoless double beta decay. This is a key process in neutrino physics. Its amplitude, as induced through the exchange of light matter and a neutrino, is expressed here it involves 3 mass parameters, not just the 2 that are well measured in oscillation experiment. And moreover, it involves the 2 Majorana phases inaccessible to oscillation experiments. I note also that I have expressed this m beta beta in terms of our original symmetrical description of lepton mixing, far better than the PDG presentation, at least when it comes to describing neutrinoless double beta decay. Of course, you can express this m beta beta versus the absolute scale of the neutrino mass or the lightest parameter m1, or recognizing that the most favorable situation for m beta beta is when neutrinos are nearly degenerate. You can invent a parameterization in terms of the degeneracy parameter, and that's the one I show here. It's an unusual presentation, but good for my purposes. You express m beta beta versus a dimensionless parameter eta, so that when eta is 1, this black line, neutrinos are strictly degenerate. To generate oscillations, you must depart either to the left, that's the normal ordering branch, or to the right, that's the inverted ordering branch. From experiment, we have, of course, searches for neutrinoless double beta decay. I show here the Kamlan-Zen restriction band, the horizontal brown band. And we have performed a recent analysis of cosmological data from the CMB and others. And these, by themselves, they rule out this vertical band, quite fat, that you can see here on the plot. So altogether, the near degeneracy possibility is strongly disfavored experimentally. So the next favorable case is one in which one of the neutrinos is massless or nearly so. This actually emerges in a variety of standard model completion to include either neutrino mass or dark matter or both. So in this case, m beta beta, first of all, has a lower bound, even for normal ordering, in contrast to the general situation. Moreover, if you lie in the inverted ordering branch, you have a guaranteed discovery of neutrinoless double beta decay in the next round of experiment, because of the tight prediction of this genetic pattern, let's say. And by the way, you have the possibility of probing the Majorana phase for the first time. What if all neutrinos are massive, though? In this case, genetically, one can have a destructive interference leading to a cancellation. However, and this is a legacy from the oscillation experiment, UV complete models that try to explain the pattern of mixing seen in oscillation experiment often lead to lower bounds for the neutrinoless double beta decay amplitude, even if the ordering is normal, as shown on this slide taken from this recent JHAP paper. You see, for example, from the right panel, that the preferred value lies very close to the current sensitivity of Kamlan-Zen and right inside the band, which is interesting for cosmology. A positive discovery of neutrinoless double beta decay would mark a breakthrough in particle physics, and that connection is established by this black box theorem, very old, almost 40 years, which states basically that observation of neutrinoless double beta decay implies that at least one of the neutrinos is Majorana. Now I move to theory proper, the origin of the neutrino mass. And first, I put down here the photo of Majorana to indicate that the most general expectation we have for what is the nature of neutrino, the answer is Majorana. And there is this beautiful argument which says that even if the standard model has no neutrino masses, one can construct a unique dimension 5 operator involving the lepton doublets and the Higgs doublet responsible for symmetry breaking, so that below the symmetry breaking scale, you generate a Majorana mass for neutrino. However, this is far from a theory of neutrino mass. To go any further, one needs a UV completion of this argument, and perhaps the seesaw mechanism offers the most interesting class of UV completions. There are many. Basically, from my point of view, due to the fact that it offers a possibility for a dynamical understanding of the small neutrino mass, following just by minimizing the Higgs potential. Moreover, this may hold the key to the understanding of the stability of the electroweak vacuum. So this can have perhaps profound theoretical consequences. Within a seesaw scenario, neutrinos acquire mass either due to the exchange of heavy right-handed neutrinos or through the exchange of heavy triplet scalar boson. In fact, it is anecdotal here that are in our original seesaw papers of 1980 and 82, we called the triplet seesaw as type 1 for the simple reason that it is the simplest seesaw. I will come back to this later. Moreover, there were other differences between our formulation and the formulation in yellow concerning the type 1 seesaw. Namely, we formulated the seesaw just in terms of the standard model, while the yellow seesawers formulated their seesaw in terms of left-right symmetric theories. In left-right symmetric theories, you must match the number of right-handed neutrino to the number of left-handed neutrino by gauge symmetry. Within a standard model type seesaw, the number of singlets is completely arbitrary. And this implies that you can have a theory, which we call missing partner seesaw, in which one of the three left-handed neutrinos do not have, one or two of them, do not have a right-handed partner, hence the name. The 3,2 possibility provides the minimal viable type 1 seesaw, while the 3,1 provides the template for the minimal dark matter completion of the seesaw mechanism, which we dubbed Scotto seesaw. It provides, in fact, the simplest dynamical theory of neutrino oscillation. Conversely, one may have more singlet neutrinos than doublets. For example, 3,6 is the case that we add two singlets sequentially to each family of left-handed neutrino. This provides the template to formulate low-scale seesaw either within the inverse or linear seesaw realizations. The idea here is very simple. You have this Feynman diagram here. Forget the blob for the moment. The idea is that if you impose the conservation of lepton number, you have that neutrinos are massless exactly as in the standard model. However, in contrast to the standard model, lepton flavor is violated and neutrinos mix. Moreover, CP is violated in the lepton sector, though the neutrinos are degenerate. So this provides a very interesting and simple extension of the standard model, which elucidates the role of symmetries in weak interaction physics. But beyond the conceptual interest, there is a practical interest. Because if you break the symmetry a little bit through this blob in the hidden sector, coupling this singlet lepton, then lepton number will be slightly broken. And if you go to the symmetry limit, then neutrinos will become massless. But there is a symmetry protecting the small neutrino mass, which is opposite from that which works in the high scale seesaw. But this construction is as natural as the high scale seesaw mechanism, with the difference that now neutrino masses will be mediated by a quasi-Dirac heavy neutrino, which can be at the TeV scale and hence accessible with colliders. You also can have lepton, violation of lepton, the unitarity, effective unitarity of the lepton mixing matrix. And all of these give you a plethora of interesting phenomena that can be probed in neutrino propagation, in a high intensity facility, looking for mu gamma or mu conversion, as well as possibly at high energy colliders. Concerning the symmetry protection of the low scale seesaw, it can actually be a double protection if you arrange for this blob to arise from a calculable radiative correction associated yet to another layer of physics, for example, left-right physics or dark matter physics, then you can have actually a double protection. In fact, yesterday there was a very nice talk by Sanjoy Mandal in the BSM section. I invite you to go there to see the details of this construction. Basically, the idea is that this lepton number violation arises, which seeds the neutrino mass through the low scale seesaw, comes from a dark matter sector, so it provides the relic dark matter density, as you see here on the left panel, indicated by the Planck measurement, for very reasonable values of the WIMP dark matter mass that you can see here plotted. This is really a WIMP dark matter, so it can be detected also through nuclear recoil like any other WIMP, such as those that come from SUSY. But this WIMP has nothing to do with SUSY. This WIMP makes it possible for neutrinos to be massive. That's its basic role. And in contrast to other scalar dark matter models, ad hoc models, here this WIMP seeds the neutrino mass generation, so it can be probed in neutrino physics. For example, searching for mu T gamma. You can see here in green the predictions for the branching ratio mu T gamma compared with the current bound from MEG. So much for Majorana seesaw. Now I move to the Dirac possibility. So I put Dirac's picture here. I changed my avatar to indicate that everything that you can do a la Majorana, you can also do a la Dirac. And this is type 1 Dirac seesaw mechanism. And you can see you go from new left to new right. So this is a genuine Dirac mass term. And the basic idea is the same as always. You need symmetry protection. First, to justify the small neutrino mass. If you are in the high scale regime, as this case, then the scale associated to the mass generation must be large. But you also need the symmetry to protect the Diracness of the neutrino. In this particular example, taken from this reference, the symmetry that makes the neutrino to be Dirac fermion is actually the Peccei-Quinn symmetry. This is Dirac seesaw. But you can also have Dirac seesaw realized a la type 2, either through dimension 6 or through dimension 5 operator. All in all, all the operators that can make this possible have been classified. There is a bunch of references here, very arcane subject. I don't want you to read at the moment, just to know that people have done theorists have done their homework, and also there have been many UV completion of this argument. And for the moment, Dirac seesaw is a possibility because we have not detected the neutrino's double beta decay yet. Now, I promised to tell you more about type 2 seesaw. I mentioned that we called it originally type 1 because it was the simplest, and it is the simplest. Here, we basically take just the neutrino mass, add this triplet guy, and it acquires an induced expectation value, very small, and this leads to the Majorana mass. You can have a small mass either by having this guy heavy or having the trilinear coupling small. We choose the second possibility. So this model is so simple that you can use current oscillation data to deconstruct the neutrino mass matrix so that neutrinos can be tested not only at low energy experiment, like neutrino as double beta decay search, or high intensity machine for mu-E conversion, but also in the domain of high energy colliders, such as, for example, the LHC or the FCC or CLIC or ILC. In principle, any of these can allow us to probe very small parameters, such as the value of the neutrino mass. I will now illustrate to you how this can happen with a very fresh example, which is still to appear in the archive. I take the case of E plus E minus collision. For example, the ILC with 3 TeV center of mass energy. And you can have E plus E minus collision to a 4-lepton fermion signal. You see here the cross-section in femtobarn, and it is plotted, guess what, versus the value of the lightest neutrino mass in electron volts. Between electron volt and 3 TeV, there are more than 12 orders of magnitude. But yes, the measurement of the fermion signal can probe the value of the neutrino mass and can probe the mass ordering of neutrino, whether you have normal ordering or inverted ordering, one of the main open issues in neutrino oscillation physics. Further, you can do the following. You can also have a 4-lepton signal in which the final state lepton is not a fermion, but has an electron in it. So it is a lepton flavor violating 4-lepton signal. And here I plot the cross section versus the branching ratio for mu-2 gamma, because this process violates flavor. So I compare with an observable that violates flavor, and the most popular one is the branching ratio for mu-2 gamma. So you can see that the cross section has a magnitude similar to the lepton flavor conserving cross section. It is also close to 10th of a femtobarn. It is not orders of magnitude suppressed with respect to the lepton flavor conserving case. And you see that the value of this cross section, if you look at the blue line, can be close to 10th of a femtobarn, well below the values of the branching ratio for mu-2 gamma that are probed by MEG. The bottom line is that high energy physics collider can provide the discovery site for a new phenomenon in high energy physics, namely charged lepton flavor violation. So far, we have only detected in nature neutral lepton flavor violation in neutrino oscillation, not charged. You may be able to find the charged brother of the same phenomenon at the ILC or the LHC. You can do a similar calculation for the LHC. Now I turn to the flavor problem. Here the standard model lacks an organizing principle in terms of which to describe family replication, why we have 3 copies, fermion mass hierarchies, and mixing pattern. And at this point, we should recognize the important legacy of oscillation experiment. Not only they have demonstrated that lepton mix, but also that they do so rather differently from the way quarks do within the CKM model. And in trying to explain this from fundamental grounds, we have come across a whole bunch of theoretical construction, a very arcane subject I will not bother you with, but just to tell you, looking from above, from a drone, that many of these theoretical extensions share a common, very simple, common prediction I boxed here in red. Very simple formula that I call golden quark-lepton relation. And it is so simple and so good that I guess that it may form an ingredient of an ultimate theory of flavor capable of explaining not only the mixing pattern, but also the pattern of fermion mass hierarchies.
Your time is ending, so please come to conclusions.
Okay. I have a couple of examples more to say that such a deep problem requires perhaps solutions that are a bit radical, and I would give 2 slides with 2 solutions, with one with 5 space-time dimension, one of which is curled, and you can give a geometrical understanding of the fermion mass hierarchies and also the mixing pattern. And apart from the abstract mathematics, you see here how this kind of scheme can be probed in double beta searches. You see here this theory prediction completely covered by this next round of experiment, and also this predicted correlation between CP and atmospheric octant. Likewise, a 6-dimensional orbifold showing how you can get, even in this orbifold scenario, the golden quark-lepton mass relation with this correlation between the bottom and tau, which I plotted here as downstrange correlation. And similarly, predictions for oscillations and predictions for double beta decay. So to sum up, neutrino oscillation experiment have brought neutrinos to the center of particle physics. There is a vibrant experimental program going on, and neutrinos may guide our steps beyond the standard model in such a way that high-energy physics experiment may provide yet another testing ground for neutrinos. Thank you very much.
Thank you very much. Thank you for an interesting overview. So we have time for the quick question. There are no questions. Okay, if there are no questions, thank you very much. And we come to